Ladies and gentlemen, a very good morning, good afternoon, and good evening to our Asia and global audiences tuning in for this event. My name is Dennis, and I head sales for Yugabyte for Asia South and India. It is my honor to kickstart DSS Asia 2024 edition. I would like to extend a very warm welcome to all of you who are joining us from around the world. This year, our summit is themed No Downtime, No Limits. Our focus during this summit extends beyond the technical aspect of distributed SQL. We are also exploring how this technology can drive business resiliency and growth in an era marked by rapid changes and increasing data demands. As we navigate these challenges together, our goal is to equip you with the knowledge and tools necessary to excel in your respective fields. We are fortunate to have a stellar lineup of keynote speakers and panelists who are leaders in technology and business. They bring insights from the world top tech companies and groundbreaking startups. I would like to express my heartfelt thanks to all speakers and participants and the attendees who make this event possible. Together, let us shape the future of distributed databases in ways that propel our business and society forward. Thank you for joining us at the Distributed SQL Summit. Let's make it an extraordinary experience. Let us give a warm welcome to Karthik, our CTO and co-founder, to kickstart the keynote for the event. Thank you very much.
Thank you, Dennis. Hi, folks. Welcome once again to our annual event, the Distributed SQL Summit Asia. And it brings back memories. It's about 6 years that we've been doing this, and it's just been growing and growing. For those of you folks who have already attended, you know what to expect. And for those of you that are joining us for the first time here, welcome. We like to keep things real, so it's going to be real issues, real use cases and real customers and users coming and talking. So this is going to be an exciting event. We're one with sharing. As Dennis said, it goes beyond just the data or the database. It's about where we're headed as an industry and the solutions and the challenges and solutions that we're putting together and so on and so forth. So let me share my screen and let's get this show on the road without further ado. So once again, it's not recorded, so you guys can ask questions. I'll actually be reading and answering. But anyways, this event is really around, this keynote is all around no downtime, no limits. Okay, so let's get started. So as we have progressed in this journey of building the database and looking at various cloud native challenges and problems, the actual explanation of what we're trying to do, what everyone's trying to do, gets simpler and simpler. So this time, what we're seeing is that it boils down to something relatively simple. Okay, so quick intro of myself. I'm one of the co-founders and the co-CEO at Yugabyte, and I'm super excited to be here, and thanks all of you for joining. Okay, so we talk a lot about being prepared. Well, being prepared or being resilient to failures is no laughing matter. It's really not a joke. It's a serious item, right? And you can take a look at how people used to think about it. It was really about being prepared just in case, right? Like you can see the just in the case. Well, today it's no laughing matter. It's really a business concern. Resilience has become like a top business concern, and a number of enterprises, large, small, big companies, small companies, everyone is thinking actively about this stuff. Okay, so if it's that important, what is resilience? What is it all about? Well, simply put, resilience is the ability of a system to respond or recover from changes, disruption, or crisis, right? And you're probably going to tell me, yes, that's true. And resilience has been around for a while. And yes, maybe everyone didn't take it as seriously, but it was taken pretty seriously by a number of people. And that has been increasing. Well, let's take a look at these changes, disruption, and crisis, right? These actually take many shapes. There are many classes of failures. There are infrastructure failures. There's like, your node, your disk, your various components failing, your region or data center outages, large-scale failures. There's errors done by users, applications, operators, so on and so forth. And there's issues arising or potentially arising from upgrades, or even the downtime that it takes to do upgrades or security patching, AMI refresh, those type of things. There are intermittent and partial failures, things that you cannot always say are happening and is very tough to catch. And there is the massive or unexpected events, spikes, etc. So there's a number of different things that go into changes, disruptions, and crisis, right? And if you remember the resilience definition, it's about handling changes, disruptions, and crisis, right? Now, traditionally, when we've talked about resilience, it is only the first two classes: infrastructure failures and region and data center outages. That's it, right? And we treat them both the same way because the scale, the type of components we use, everything was, to a point where the probability of failure wasn't too high, right? But the key point is it only addressed a couple of types of failures. And that is no longer enough, because as the scale of operations increases, everything starts to become more frequent and more common and a bigger problem. And resilience is now expanded to define more things. So we're going from the era of just resilience to the era of ultra resilience. Why? It's because the customers, the users, well, myself included, I expect services to always be on, and I'm sure you do too. If an application or a service is down for a while, well, I'm probably going to switch to a different application or a competing application, something else. The second insight here is that entire nations are now running on digital infrastructure. Think about the banking application. Think about your credit cards. Think about like your digital payments, your online payments, like online shopping, like maybe tax returns. Everything is being done online. So nations run on digital infrastructure, and when a nation runs on it, resilience becomes super critical, right? And the third thing is the brand reputation. Unlike 10, 20 years ago, today, you would probably think, well, if a particular service or a brand or a company cannot keep their service running all the time, well, I'm not going to trust them with my most important data. Like, think about your money. If they can't keep the website up, and the service up, I'm not going to go put my money in there. If I cannot withdraw when I need it, if I cannot deposit money when I need it, I'm not going to go to this, service provided by this, by this enterprise. So brand reputation has also gotten tied to uptime. Okay, so ultra resilience. We're going from resilience to ultra resilience. What really changes? Why is this change so important? Why did we not need this 10 or 20 years ago? Well, there are three classes of things that have changed in order to make this super critical. Well, the first thing is that we've gone cloud native. And by cloud native, we have cut costs by going from specialized hardware to general purpose hardware, commodity hardware. And that means there are more failures. Commodity hardware is cheaper, but it does introduce more failures. The second thing is the operational footprint, the number of such applications running, the number of services, the scale of services, everything is getting bigger and more. And that means that even if your probability of failure is small, well, the sheer number of services is so large, you are probably going to see a failure somewhere, right? And so that means more failures. And thirdly, if you have a very successful application, you can never predict when it goes viral or when it becomes successful. But when it does, that very spike, that very unexpected event of everybody starting to use it could cause failures and overwhelm your system. So overall, we have to deal with failures, and therefore we have to become resilient, and not just resilient, ultra resilient. Okay, so failures, we're talking about failures. Don't forget that, when we go to commodity or cloud native or the cloud, well, there is a number of events that tell you that, failures are pretty common. They happen all the time. It's not because anybody is doing the wrong thing or not doing the best that they can. Everybody is, but it's just the sheer footprint. It's the sheer volume of operation that causes these failures and the cost savings that comes with using commodity hardware. So this is the new nature of the game. These are the new rules. How do you ensure ultra high resilience in the face of failures that can happen, right? And you might say, really, failures, do they really happen that often? Well, these are, this is a graph of the per quarterly outages and wide scale major outages, not small outages like, zone or regional outages in just the Asia Pacific region, right? And you can see that the number of outages that cost companies more than $1 million to recover from has increased from 11% to 15% since 2019. And this number is just going to keep going up unless the architecture works to become ultra resilient and delivers it from within, not from without. Okay, so we talked about these different classes of failures. Now it's important to recognize each of these classes of failures is a different kind of resilience, right? So infrastructure failures are really about in-region resilience. So if your node or your zone or your disk or something else in the networking stack like is off or is not working or has an outage, well, you have to architect your system for inside a region resilience, so in-region resilience, and so on and so forth, multi-region data breaks, and so on and so forth. So don't worry if you didn't catch it all, because the rest of the keynote is really about going into each of these, and it's not going to be just my word or somebody's word. We're going to point you to sessions that actually talk about a number of these things. We have real examples and real users that have come in and architected systems that work around a number of these failures. Okay, so here are the 6 elements of ultra resilience. These are the 6 classes of things we talked about. The first one is in-region resilience. The second one is multi-region business continuity DR, shortly known as BCDR, to ensure that you can survive an entire region or data center outage. Then there's data protection to make sure that if you drop that table by accident or some data gets corrupted, you can recover from it. There are zero downtime operations, which is also an aspect of resilience. Then there are gray failures, the things that are hard to pinpoint. And finally, and most interesting, like from an entertainment value, are the peak and freak events, things you thought would never happen and that will manifest themselves as failures. So let's go into each of these, right? Let's take a look at each of them. But before we get started, it's really about ultra resilience giving you no downtime and no limits. So sometimes you have to worry about peak and freak events, and you have to put limits on what you're able to do as a business or as your application. And the aim of where we're headed as an industry is to be able to deal with failures without imposing limitations, right? And of course, keeping costs in check. Okay, so all of these 6 elements gives you ultra resilience. So let us dive into each of them. Okay, here's number 1. We talked about in-region resilience. So let's start with that. Okay, firstly, what is in-region resilience? We alluded to this a little bit ago. Now, we talked about how, like, when you're running inside a single region or a data center, you could have a disk fail, a node fail, an entire zone fail. You could have network partitions. You could have your actual software process that's running that can fail. Now, each of this you have to be able to deal with and at scale, because the number of your disks, nodes, the zones are pretty constant, but the number of services running inside a zone, the number of flaky network partitions, the number of backend processes that crash for a variety of reasons, they keep going up because the number of services deployed and the scale keeps going up, right? So how do you do that? Well, firstly, it is important to recognize what can go wrong. The most important takeaway here is, compared to 10 years or 20 years ago, or even compared to custom components in data centers, on-premise data centers, both public and private clouds have a very high magnitude, an order of magnitude higher probability of in-region failures compared to all other classes of failures. That means that your node, your disk, your zone, your network partition, one of this is going to fail, probably this quarter, and pretty often, right? And so these could be transient failures. It could come back in a short period of time, or they could be longer failures lasting for a duration, and they may or may not heal automatically, right? And it's important to recognize that it cannot be a fire drill in order to deal with each of these failures, because they simply happen all the time. Now, what do you want from this, right? Ideally, you want to think about not losing data, because you write that application, you don't want to deal with what the application will do if you lost a little bit of data. You want to recover very quickly. Ideally, the user doesn't even see the failure. The service is running fine, and it's automatically handled. I don't know how many of you folks have actually been woken up at 3 a.m., but I have, and I can tell you it's not fun dealing with failures at 3 a.m. or 2 a.m. in the late at night, early in the morning. Well, maybe if you're up all night, that's a different issue. But I actually like my sleep at 3 a.m. So why do traditional database architectures not work? So let's take a look. So what do you do with a traditional database like an Oracle or a Postgres? You take async replication And you either make it work like async replication or you make it work like sync replication, writing to both sides. And you place each of this in a different zone because you want to be able to have, zone protection. You have to have your data across zones. But your problem at this point is if a zone fails, if the primary fails, how do you automatically handle it? Because this is a manual system. And believe me, a lot of people are still doing this with various different scripts and patchwork, right? Now, the simplest solution is to build an application, or perhaps somebody like Oracle will give you an application that like called an observer that's going to take a look at if the primary failed and promote your standby or replica to the new primary, right? There's no standard solution for Postgres, and these solutions come with their own challenges, right? So now this is your traditional active single region architecture, right, for a database. Now let's take a look at the common architectures, common failures that we talked about, node, zone, and impose them and see what happens, right? We'll go pretty quick. So let's take a node failure. Well, you could have your primary failing or your replica failing. If you're doing async replication and your replica fails, and your primary fails, and you have to promote your replica, you could lose data. And you now have to deal with what happens if I lose data. Is this going to be a real impact? It could be that user that deposited a $100,000 check, and that was the data that was lost, and you have to go through to reconcile all the data, so on and so forth. The second issue is if you're doing sync replication, and let's say your replica fails, then you cannot write because you are synchronous. So you have to take higher latencies, unavailability, your writes failing, all of that stuff. Okay. Now, your second issue on a zone failure is what happens if the zone in which your observer sits fails? Well, you could move it to one of the two other zones, but it causes a lot of problems with intermittent network partitions and so on and so forth. So your automatic failover is really compromised if your zone fails, if the zone in which the observer sits fails, because it's not a symmetric setup. And lastly, when you have a network partition, you have a split brain scenario. So the primary and the replica cannot talk to each other, right? And what do you do? So in this case, if you have async replication and your primary and replica are split, then you could have a divergence. You could have your primary taking some stuff and your replica not having all of that stuff, and you could get in trouble. And with synchronous replication, you could have, like with a network partition, frequent high latencies and your P99 fails and so on and so forth. I see a question in the chat, which is a YugabyteDB Oracle RAC active concept. Yes, we do. We have a lot. This is similar to what we're talking about, Chiravuri. So yeah, so we do have that. But please feel free to ask us, ask more questions. Someone will hopefully answer. So let me keep going. So the fourth problem is around application architecture. Now, what happens when you have a primary and a replica? Well, we all know that the application must be aware of what is the primary, because the replica can get promoted. That's problem number one. And problem number two is that your primary nodes can serve consistent reads and writes, but your replica or standby is just doing nothing. And nobody likes hardware that's doing nothing. So, in order to do that, you get your application to read from the replica, but they are stale reads. And now your application gets more complex to figure out, can I do a stale read for this particular query or not? Or is this really has to be consistent, or so on and so forth, right? So it makes it more complex. Now, if you go to a distributed SQL architecture or an architecture that embraces in-region resilience inherently, you don't have this issue. So with something like a YugabyteDB, you have raft consensus, a consensus algorithm doing replication across the three zones. So you have one copy of the data in each of the three zones instead of two. And the algorithm internally looks for which two of the three, a majority, are able to see each other and are available in order to detect what piece of data is consistent and where to serve it from. It's all automatic. So that means if a node fails, you're totally fine. Raft handles this inside the region. Your failure is auto-detected in about 3 seconds, and somebody else will take over. Your traffic is instantly fails over to the other nodes. And once the node comes back, you don't need to do anything. The system will automatically bootstrap the first node in zone A. So, no more waking up at 3 a.m. to figure this out. No more having to do anything manual, even at 10 a.m. because the number of these incidents could be quite high. Okay, the second thing is around the simplicity of the application design. Because you can read from any of the three any of the three regions, any of the three zones, any of the three nodes, your reads are all consistent, your writes are all consistent, all nodes are evenly utilized. So a failure just means send the read or a write to a different node that's available, which is very, very easy to accomplish, and all nodes are evenly utilized. Okay, so essentially, what you get by embracing cloud native is a much superior design with in-region resilience. So that means you don't have to worry about exercising, disaster recovery or anything manual if just a failure happens inside a region. And believe me, you can look at the stats. The frequency of failures inside a region are simply orders of magnitude higher than all of the others. Okay, so don't take my word for it. There's a presentation by Navi, which is a system of record for Unified Payment Interface (UPI) in India, and they're using YugabyteDB and doing about 500,000 transactions a day, and they're looking to grow to 30 billion monthly transactions. So big numbers. And one of their key goals in resilience was in-region resilience, 24/7 availability, while being cost-effective and operationally simple. Right. So do take a look at their session. It's one of the sessions coming up in the day later today. Okay, so that brings us to the second topic, which is multi-region BCDR, business continuity DR. And let's go really quickly as to what is BCDR. Well, with BCDR, you get the ability to survive an entire region or data center failure and continue your business even if that happens, right? And you could have a power grid fail, you could have natural disasters, and it's becoming a part of regulation, because when countries and economies depend on digital services being available, it's super critical to be able to survive these type of failures, because it can bring the economy to a grinding halt, right? And so it becomes a part of complying with regulations in order to operate at that level. Okay, so what can go wrong? Well, you could just lose an entire region or data center. It's low probability, but remember the opening slide, just in case is not the option, right? It's like putting the just in the case. That's not the real option. It's got to be working. You got to know it happens, right? What to do when it happens. And these failures last a while. They are complex, and it needs to be able to heal once it comes back. So it's like an entire region goes down. When it comes back, well, what happens? It cannot be a multi-week or a multi-month effort to get back, right? So what do you want in these scenarios, right? On the right, we talk about it. It's really the ability to trade off between performance in the steady state and your potential for data loss. So everybody wants to lose no data and lose no performance. There's a little bit of laws of physics that kick in. So the question is, do you absolutely want to lose no data while giving up a little bit on performance? Or do you absolutely want the performance and you're okay giving up on a little bit of data? But no matter which way you go, you want quick recovery, and you want to be able to test the system on a periodic cadence. It's just like that fire drill, testing. You have to be able to know that when the time comes, this thing works, which means you have to keep doing planned switchovers without losing data multiple times, right? And this also is a part of regulation. Okay, so how do we think about this? So let's peel the onion a little bit here. Well, there's the application architecture and there's the availability architecture. How is your application going to function, and what are your availability goals, right? So if you think about application architecture, there are three different ways to think about it, three different aspects to this. You could have your application working only in a single region, so it's single active. So in this case, for example, you see that the application is active only in, say, US Central and standby in the other two regions. And when if you have your application running on all the regions, you could have all of them reach this data in a single location. It's multi-active. It doesn't matter where the data is. The app is active everywhere else. The data can be wherever it is. And the third option is your data set itself is partitioned. So you have people living in one country versus people living in another country, and your app actually accesses data local to the location in which it's running, right? It's still a single cluster, a single logical database, but you want to access local data most of the time and remote data sometimes, but with higher latency, right? So these are your three options. And don't worry if you didn't catch it, we'll summarize it in a table. In the availability architecture side, there are two options. The first one is, you have your application running here in US Central, like right in the middle. What happens if it fails? Well, you might want your entire app and data to move over to a different location, in this case, US West. So everything moves in one shot. And we're calling this pattern follow the workload. So your workload moves and the data follows it. So it's a follow the workload pattern. And your other option is called a geolocal data set, where what you care about from the data point of view is just make it highly available inside a geography. Don't need to move with my workload. And you'll make the workload highly available inside that geography, and you can mix and match. So in this example, you have an application running in the US and you have another application running in Europe. All of the data here is being accessed in the US, and this data is in Europe. If this zone dies or this region dies, you have your app continuing to access it in the US from somewhere. It need not go in lockstep. It could be like, the app on one side and the data on the other. As long as it's in the US, you're okay, right? So this pattern of availability, we call it geolocal data set. Your data set is local to a geography, but highly available. Okay, so if you put it all together, the three different application availability dimensions and the two different application dimensions, architecture dimension, the two different availability options, well, you get a table, and now you want a way to achieve that end goal. So for example, you want your single active and follow the workload, or partition multi-active and follow the workload, right? And so this gives rise to a number of different design patterns where you want trade-offs. You want to say my latency has to be low, but I'm okay losing a little bit of data. My latency I'm okay with the latency being a little higher, but I don't want to lose any data, and vice versa, right? So this gives rise to a number of different design patterns that you can achieve. Now, the important thing to realize is that a traditional database, takes care of 2 or maybe 3 of these, right? Even read replicas are pretty hard to manage with a traditional database, but there's only about 3 of these that you can achieve. And those 3 are actually made simple by a distributed SQL database like YugabyteDB, because replication is built into the database, right? And while it enables a bunch of other patterns, right? Like 5 or 6 unique different patterns, and that makes it a lot easier to accomplish your business goals. Okay. All right. So the next thing is around like global deployments and async replication and read replicas. This is a single application pattern, right? So in this theoretical application, we put one cluster with the data in one region, asynchronously replicate the data to another region. So this is like your traditional asynchronous replication between clusters. Each of the cluster is running multi-zone and is highly available in region. And you have a bunch of read replicas across the globe, right? So 2 data centers or regions with asynchronous replication, and 3 other regions with read replicas to reduce the latency, right? Now, this is not a theoretical model. In this model, we took 3 of the design patterns that were shown in the previous slide and put them together in order to achieve a very interesting business goal, right? And if you want to learn more about this, go to the Airwallex talk, because this is actually their design pattern. This is what they actually implemented and deployed. They are a global payments and financial operations platform. And multi-region resilience was their primary goal, continuous global operations and consistent data, distributed data, low latency access, and so on and so forth. So that entire set of patterns working in tandem, that's something that they've done. So don't take my word for it, go check it out. All right, there is another use case that's quite interesting, that's also multi-region. This is with SKA Observatory. So this is a very interesting, cool use case. They're getting data from telescopes, and and they do the observation across 3 different sites across the globe, and they need to share data across these 3 regions, which actually get data from the stars. So shooting for the stars, but more literally. And it has 3 sites with follower reads, row level geopartitioning. It's deployed inside Kubernetes. A lot of interesting challenges here. So do go and check out their talk as well. Right. Okay, so that brings us to the third element of the ultra resilience pattern, which is data protection. All right, so What is data protection? Well, it is your standard backups, point-in-time recovery, also shortened to PITR, software rollbacks, blue-green upgrades, etc. Right? So why is this pattern important? Right? This pattern is important because many times the issues that lead to your failure are not infrastructure component or the data center issues. It's more that the data being written is corrupted or is bad, or there was an operator error, or an application got a poor, like a bug in the code caused something to get corrupted, or so on and so forth. And being able to recover from that in a systematic and timely manner with ease is actually a super critical part of resilience as well. So let's talk about each of these really quickly. So backups, right? So we all know, backups are super important, like as in for a traditional database, because you have the database and if it goes down, you go to the backup to fetch data. Well, in a distributed database like YugabyteDB, you have multiple copies. So do you really need backups? Well, it is important to have backups, like mainly to recover from, a variety of different data corruption scenarios, like where the database is fine, but the data that the application wrote, so the app has a bug which corrupts data, or a variety of such issues, right? As well as to comply with regulations and audit, like you want to retain data for a particular time window. You want to make sure that you're able to restore to a test or dev, or a staging system in order to test upgrades to your software, so on and so forth, right? So yeah. And consistent high performing backups are very, very critical. So think about some of these aspects when you think about backups. You want your backups to be periodic and with configurable retention. So nightly backups for the last 8 days, maybe perhaps hourly backups, or more frequent backups in some cases where you would need something like incremental backups to make it efficient, as well as encrypted backups to make sure that, because your digital footprint is increasing, you want to think about the security aspect of it. So if somebody gets hold of your backup instead of your live data, well, you're still secure because it's encrypted and they can do nothing without keys, right? And make sure that while taking a backup, it has low application impact, and make sure that in multi-region deployments, your backup is actually done locally in each region, because sometimes there's a performance aspect why you want this, and sometimes that there's a regulatory aspect why you need this, right? So if you have a database that's spreading multiple regions and you're running it on, say, AWS, make sure it goes to the S3 bucket that's local. And if it is a private cloud, then it goes to the appropriate NFS filer or something where you keep your backups. Okay, so ability to back up quickly is something that is super critical. This is the rigor that we're putting ourselves to, so YugabyteDB to. So we're able to secure and back up data in just 11 minutes, and this is a pretty large 15 terabyte data set, and it's replicated 3 ways. The backup size is 5 terabytes, logical. So we're able to back it up to AWS S3 in region in about 11 minutes and restore it in just over 30 minutes, right? So the speed will help, right? Like if it's no use, so because the RTO has to be low in modern times, it's no use if their backup is there, but it takes forever to do it, or the restore takes forever to do it, and especially with increasing data set sizes. Okay, let's go to the next topic, which is point-in-time recovery, PITR. And for those of you who don't know what this feature is, it is the ability to roll back a database to a point in time in the past. So move my database back an hour, or move it back as of 7 a.m. this morning, or whatever it is, because that some issue happened around that time, like you got a software upgrade which caused issues, or something else happened, and you want to be able to go and recover from that error, right? There are 2 classes of errors: user error or software or application errors. So like, for example, I know, or I've been in real scenarios where somebody connected to a cluster and thought it was their test environment and their dev environment and dropped a table, and it turned out to be production, right? And so it is very critical, because errors often happen, and especially when when the footprint increases, the probability of errors increase. So being able to recover from that, being able to recover from an incorrect schema change, an accidental schema change, a badly written row, or some corruption that came in because the application had a bug, all of this stuff is super important to be able to roll back, right? And So some of the things to think about is that the database should be able to provide both, the point-in-time recovery on the cluster, like live very quickly, as well as to be able to restore it to a remote cluster and then do the point-in-time recovery there. Right? There are two different use cases, and the ability to do that on the cluster, at least with no data movement or copy of data, especially for large data sets, is super critical. And it should be easy to manage, not just from a UI, but also from a REST API for automation and a variety of different things. Because when the need to exercise these things hit, there's often a huge time pressure, and it's important to be able to do that efficiently. Okay, so let's take a look at a simple example of recovering a dropped table. So let's say you have 6 tables in this theoretical database running across 6 different nodes, as shown in the picture, right? Nodes 1 through 6 and tables 1 through 6, and that's DB1, database 1. Now, let's say we dropped table 4 accidentally. So, table 4 is no longer there, but it's still retained because the point-in-time recovery is enabled on this cluster. So table 4 is soft drop. The data is still around, but you're not going to see it. Now, somebody realizes, oops, that was not my dev cluster, that was production, I need it back. Well, the minute you realize this, you're counting seconds and minutes in order to recover, right? So it's important to be able to quickly, with YugabyteDB, you can do this, you can quickly clone the database, right, very quickly. And so the way it does it is it takes a reference to the existing data, it doesn't copy the data. So it's just like making references to a bunch of files and quickly creating a DB1 clone, right? And we go from there to roll the DB1 clone back to before table 4 was dropped. So in this, now suddenly table 4 is visible because it's a clone of the data that's not visible in DB1, but is still visible in the clone, which is now point in time restored to before the table drop. And you can quickly copy the table from the clone of the DB1 to the actual database, and you have restored it pretty quickly, right? So it's a very clean and simple workflow, and you can do this in a matter of minutes. And so that usually, the ability to do this is super critical when the issue hits, right? And similarly for all other use cases of point-in-time recovery. Okay, the next thing is around rollbacks. So rollbacks are important because you upgrade the software and things don't work as expected, and you want to roll the thing back, right? Like you have unexpected behavior with a variety of different things. Like your upgrade itself is, you encounter issues due to the surrounding environment, due to the database, due to some say query plan not working as expected, latency is not working, a variety of different reasons, right? And so like this is a feature that we had to specifically introduce, and it requires a reasonable amount of engineering in a distributed system to be able to upgrade, keep it in a state where you can roll it back, and finally, once you find everything is working okay, finalize it before, right? So this is another thing that a piece of resilience that's super critical to think about, right? And and lastly but not least, there's the blue-green upgrades, which de-risks the upgrades a lot. So in this model, you have two instances of the cluster, and your application is running against one, and you upgrade it, and you have a standby or like a replica that is running the older version of the database software. And if you encounter issues, you can always switch back to it, right? And so this is really the way to truly de-risk your upgrades. And what cloud does, the public clouds do, they make this very, very easy, because you can create your green cluster on the fly. So you create a blue cluster, you have an original cluster running, you create a new cluster, and you run blue-green for a week, and then tear down the blue cluster, and you're done. So this pattern means you're not really incurring a lot of hardware costs sitting around. You're just doing it for the duration of the upgrades for the week that you're testing it, and then you let go of all of the hardware resources. And so something like YugabyteDB and its deep as database as a service around it really makes all of this simple, right? So I think to put it in the form of a picture, you have an application that's running against US West, and you create a replica, or you maybe already have a replica in US East, and you upgrade US West, make it the green cluster, and your app is running there. And now you have two cases. After the upgrade, your app is working perfectly fine, in which case you go ahead and upgrade the East cluster as well. Or your app is not running okay, in which case you fail over to the blue cluster, roll back the green or figure out what needs to be done with it, and you can go from there, right? If you fix and reiterate, right? But it's important to have that safety mechanism as a form of resilience. Okay, so there's a talk about XIgnite. It may not exercise all of the stuff that we talked about, but it's definitely like the XIgnite is a they deliver, they're a fintech, like a financial tech star like company, and they deliver real-time and reference financial market data like stock tick data, all of that stuff, like for other financial institutions to consume. And you can take a look at how they're dealing with flexible upgrades with zero downtime, data consistency, scalability, etc., etc. Okay, so let me keep going. There's zero downtime operations, so I'm going to speed up on some of these. So in terms of zero downtime operations, your usual software upgrades, OS patching, changing the machine type, changing instance types, security key rotations. So what do you want? You want nobody to know it's happening. It just should be transparent, right? So these are reasonably frequent operations. Everyone's doing them on a clock pretty routinely, but you want to know, is it happening? Is it progressing? Is there a problem? If not, let everything go through and don't affect the application, right? So how do we achieve this? So let's take an example. Let's take this 6-node example that we took before, and we have a database, and your application is connected to all of the nodes. And in this example, you have the data replicated across 3 of the nodes. In this case, database 2 is replicated across 3 of the nodes. And let's take the middle of a software upgrade process. You've upgraded 1 node at a time. You've upgraded the first 3 nodes, and you're now on the 4th node, which is in progress. And databases 4 and 5 are being served out of this node, right? So what do you do in this case? First, you drain the traffic from node 4, right? That means you move the traffic to other replicas. And once that is done, you drain the traffic as well so that it starts going to other nodes. And so this node is now sitting around and ready to be upgraded. And you can go ahead and upgrade it, take down the the process, or even security patch, OS patch, AMI refresh, whatever it is you want to do. And once that is done, that node is back, and it will get back some of the databases that it was serving, and you can keep doing 1 node at a time, right? So take a look at Jakarta. Like they deliver IoT systems inside a single region, and they do it is a service to monitor Jakarta's water networks and flood systems, and they're doing full online operations with full automation while retaining all of the power of Postgres features. So do check out their talk on that. Okay, we get to the last 2 topics: grave failures. It's an interesting topic. Grave failures are things you cannot catch very quickly. They happen and they go, and they keep happening, right? And once they happen in enough frequency, it's really a pain, but it's very tough to track down. So performance degradation with spikes, random data delays, flaky I/O, thrashing, noisy neighbor, all of these can lead to grave failures. It is one of the Achilles heel of most public cloud systems today, and it's like you're not sure if it's good when it works. It's better when it just fails outright, but it's very hard when it's like kind of not working every now and then, or so on, right? And so these are subtle to diagnose and root cause. And one of the key things with data resilience, and this is one of our key design principles, is that we care about detecting these, even if it's not our problem, because ultimately it's about delivering resilience, ultra resilience, on top of fundamentally commodity hardware, where failures are the norm, even grave failures, right? So like an example is very, very rare, but it does happen. Your EBS grayouts, where your EBS volumes can sometimes not respond with it won't fail outright, but it won't respond. It'll hold the write and it'll just hang, or it'll take a very long time to respond to your write. So in these cases, the database as well as the software around it actually detects these scenarios and handles them, and invokes the resilience code path by either forcing the termination of the nodes that are impacted, or alerting, or a variety of different approaches. But it's important to think about this. I mean, there's a number of different examples. Like, for example, there's one protection that we had to put where your DNS system could be flaky in the cloud, and you should not initiate a software upgrade during the time, because after a node restarts, it's going to contact the DNS system, which is flaky and not working. But if you just leave it alone and do the software upgrade at a different point, it actually is pretty safe. Okay, let's keep going. this is the most fun to talk about. So peak and freak events. So let's talk about what these are. So, there are unexpected bursts, right? You'll get more success than you expect. You know that you're going to get a lot of traffic. You just don't know how much. So you can expect a peak and not know how much. You can get hit with an unexpected peak, or you can get hit with things like DDoS attacks where someone's trying to take the service down and you still have to write it out because it's super critical. A variety of different things can happen here. So let's look at a couple of these unexpected failures or disasters and a couple of expected spikes, right? And then take a look at them. So this is a top 5 global retailer that is using YugabyteDB. And they're using it to serve their product catalog of over 1.6 billion products. And for example, like Apple releases a new iPhone or PlayStation releases a new version of the PlayStation. All of these are super spike events, right? But that's not what we're talking about here. It's important for everybody to be able to get to them. But one of the freak events was a snowstorm in Texas in the US that took out a cloud region because it took out the power grid for 4 days. There was no power, right? So there's no data centers were working. And their challenge was to keep the product catalog up and running during the entire peak season, during the holiday window, and to sustain their throughput and keep their latencies and everything under control. And they were able to achieve this. But here's an example of fundamentally building reliable ultra-resilient services on top of a inherently low reliability commodity hardware system, right? So okay, so let's go to peak scale, right? Here's an example of Paramount Plus, which is like an international brand. And they use YugabyteDB as their database to authenticate users and to get access to the video stream. So, what is your profile? Are you allowed to see something? If you're paying, process the payments, etc. And so their business objective is to get the data and their access to the data, including their identity system, closer to the users through a multi-region cloud deployment, as well as keep users' data local to the geography to conform with security laws. So they recently had a huge peak event. They ran one of the biggest live streaming events ever in the US, and this was the biggest. This was most watched with over 120 million users at a single point, and over 200 million users total logging in to watch the thing. And the interesting thing about events like this is that right before the event, everyone is logging in. They are hammering the database to all get access to the stream, and they may log out or log in during the halftime. There was a famous singer, Taylor Swift, who came and sang, and the bunch of people would log in to see that. So there are spikes that keep happening throughout. And it's not just this event, it's any major sporting event, any major media event, they cause a lot of spikes. So the ability to handle that is equally a part of resilience. Okay, let's talk about unexpected spikes, right? So spikes are good. You want these spikes. You want more people using your application, and the business usually is a success if that happens. But your prediction may not be equal to what happens in reality. So your prediction may be that a couple of your applications may get high in volume. The reality may be completely different. A variety of different applications become popular. The business focus shifts. Everything can happen, right? So it is often important to take care of scaling in quickly for unpredictability, right? And so, there's a lot of talk around, should you do horizontal scaling? Should you do vertically scale? Well, it's more important to understand that the scaling has to be seamless. The application should not know. And there are different characteristics to horizontal versus, vertical scaling. But whatever it is, the scaling operation itself has to be simple. An API, observe the progress, and be informed when it's done, right? So it's as simple as that. Okay, so you can take a look at the talk from Singtel about how they are surviving peak and freak events. And they are a customer engagement platform, and they store critical user identity data and customer profile information. And they have monthly billing surges, especially during these launches, right? Apple and Samsung phones and so on. And how do they handle it? Very similar to our Paramount Plus story, right? Another example is General Motors. They have a fleet of vehicles, General Motor vehicles, that send back data, and they're converting all these vehicles to smart vehicles and powering For example, you make an emergency call, like a roadside assistance call. Well, that has to go to a system that has high resilience, because you don't want that call to get lost. You want it to be treated, responded to and taken care of quickly. And similarly, like insurance, remote entry through your cell phone, you want to open your car, start the climate system in the car, so on and so forth. So they are getting data from 20 million plus vehicles, and that translates to over 3 million writes per second, and over 70 terabytes of hot data, with over 300 to 400 terabytes of total data, and a number of applications being built on top of these systems, including pretty important critical systems such as the emergency roadside assistance calls. So these are examples of surges that can happen, because you never know when what would happen, which would generate more data, who would sell more cars. Like, it's just tough to predict these scales, but it is important to be able to grow to such scales. Okay, so net, remember the 6 elements of ultra resilience that we talked about today. We went through a fair bit of detail. There are a lot of good sessions that talk about all of this and much more. So, please feel free to go in, ask questions, be a part of it. But in-region resilience, multi-region BCDR, where you take care of data center failures, data protection, where you take care of app and operator errors, zero downtime operations, where you are doing stuff, all the time, upgrading software or patching nodes or, replacing refreshing the OS, but you have to do it with no impact and with ease. Gray failures, which are hard to pin down, but you still have to deal with them. And finally, peak and freak events, where it's like a one-off tidal wave can come hit you. You still have to be able to deal with it, right? So you need all of these in order to truly architect for no limits and no downtime, right? Which is kind of what we all are aspiring to do as an increasingly digital industry. So catch these amazing speakers. There's Rakuten, from Rakuten, Gaurav Jain, their head of AI and data products, is giving a talk. OCBC, Lim Wei Ming, the head of data architecture, is giving a talk. Singtel, Rishikesh Sawant, the principal software engineer, and SK Observatory, Mauricio Zambrano, who's a database engineer, and a lot more interesting talks. So do check them out. I hope you really enjoyed it. Thank you all for joining us. I see a couple of questions, and we have a couple of minutes, so I'll probably do a couple of questions. There's one which is about, how does replication work in the case of blue-green upgrades? Well, replication in YugabyteDB, asynchronous replication in YugabyteDB knows to work across versions. So the way we send the data, we keep it as compatible with the older version, with the blue version. So green sends to blue, blue sends to green. They're able to interpret, right? The one that's not upgraded would not have all of the latest features as a database, but they would be able to version match, right? There's another question around, are there any limitations or high performance issues in Yugabyte when creating N of tablets? Well, this is a tough question to answer, like in a keynote kind of setting. I think this depends on the details, a lot of details. Typically, no. What we've seen is in most practical applications where N is a reasonable number, we're able to satisfy what the application needs. But that kind of depends on the details. And there's one about, how are conflicts resolved if there's a new column in green, but the blue does not have? Is their replication defined at the schema level or the object level? Well, our replication is defined at the database level. And this is a great question. I think I don't remember off the top. This is a pretty detailed question for a keynote, by the way, so thank you for asking it. I would suggest you pop into our community Slack, or somebody from the Yugabyte support team can get to you. But there are phases in which we're doing this, and there are safeguards and limitations that we're putting in for the duration of testing the blue-green. So the blue-green is not your permanent state. The blue-green is actually a temporary state for a period of time, and you upgrade to blue-green, green-green, or downgrade to blue-blue, and you can continue business as usual, right? So there are some restrictions. It's not at it's definitely not at an object level. It's more, you can do it at an object level, but we are assuming that it's more important to do it at a database or a schema level. Okay, so there are other questions like, what safeguards are in place to prevent accidental schema modifications? First off, I really love the depth of the questions and the thoughtfulness. Like, thank you, all of you. Like, Juan, Rachel, a lot of people are asking, Manish, a lot of people are asking great questions. These are really the spirit of resilience questions. So the question is, what safeguards are there in place to prevent accidental schema modifications in the event that occur, and reversibility for data integrity preservation? So point-in-time recovery, PITR, does take care of reversing the schema changes, and we do have the ability to restrict certain type of dangerous schema operations like truncate table, etc., which you want to put in place in production, but not so elsewhere. And Ravi Kumar has a question around, when we say we are 100% no downtime for, are we 100% no downtime for maintenance activity? Yes, that's what that is our aspiration. So everything is done in a rolling manner. So that is truly where we're going. And we're adding more and more operations and runbooks and automation and APIs around it to be able to achieve it for a variety of different infrastructure substrates, like whether you're in public clouds like AWS, GCP, Azure, Kubernetes, or even through VMs, data centers, etc. I will do perhaps this one last question from Arjuna. How to DML conflict is managed in YugabyteDB? So if you're talking about DML conflict inside a single region in a single cluster, we have a distributed transactions algorithm that has a elaborate set of locks and provisional rights and a variety of different things. It's a pretty detailed topic, but we are distributed yet transactional. Okay, lot more interesting questions. I think we're probably running out of time. So what I would recommend is, folks, please join our community Slack. Do ask these questions. And I would request the Yugabyte folks to please help connect with the folks and answer their questions. But thank you all for the level of engagement and these deep questions. Thanks a lot.